Back, everyone. Just before we start, I would like to ask everyone to keep their cameras and microphones off while they are not speaking or presenting. So next in the agenda, we have a plenary talk by Dr. Cornelia Oedekoven about the use of recent advances in technology to count dolphins and whales. Cornelia is a senior research fellow at CRAM, and she started as field biologist at sea before moving into the world of statistics. So with that, I'll give the floor to Cornelia. If you can please start sharing your screen. And I'll turn off my camera.
Can you guys see everything?
Yes, we can. Oh, sorry.
Okay. Okay, so what I'm talking about today is not so much new statistical methods. Mark recapture distance sampling has been around for quite a few years, but new applications of these methods in the field that are now possible due to recent advances in technology. So a little bit about my background, which explains a little bit why I'm so interested and heavily involved in analyzing marine data these days. So I used to spend a lot of time at sea, being one of the observers, going out on research vessels, collecting data on marine mammal surveys. Here's one example, the 2006 survey in the Eastern Tropical Pacific. Sorry, where the interest was in coming up with abundance estimates of various dolphin stocks that have been affected by the tuna industry. Dolphins get caught in the nets used by the tuna fishermen and die. So in the last century, millions of dolphins have died from this practice. The practice have been changed in the meantime, but it's still a legal requirement to monitor these dolphins. So this was a line transect survey, which is part of distance sampling. And I'll explain a little bit about what this entails. So think about a very simple example where you have an observer. An observer can be one person or can be an observation platform, like a visual team on a ship. So think of that as observer one. And this observer goes along this line and makes detections of animals, the blue dots, and the detected animals are indicated by the yellow dots. And along with the detections, the observer records the distances out to these animals, the perpendicular distances from the line. It can then use these distances to create this histogram bar, which we see on the right. And you see also a detection function, g of y, fitted through this histogram. And I think now there's going to be that little box in the way. Anyway, so if you think of the area under this curve, it's the same as the area under the histogram. So this is how you could roughly fit this detection function by hand, but of course there's more sophisticated methods underlying the algorithm using generally maximum likelihood methods. So this area under the curve in relation to this green box, so the green box representing what the observer would have seen had they missed no animals, had they detected all the animals in the surveyed area, then so we can use the comparison of the two areas to calculate the proportion of the animals that the observer detected. So that's a quantity that we're going to denote with P sub A. So what is really important here, the take-home message from this slide, is that this method heavily relies on the assumption that the observer detected everything that is on or near the line. This is highly important. You can see from the left plot that the observer was allowed to miss animals that are further removed from the line, but it's absolutely essential that the observer doesn't mean anything near the line or directly on it. So these are the methods to estimate your average detection probability within the covered area. And you see up here in this slide, the estimator, how that feeds into the estimator for estimating abundance. And you see the various items from that equation explained here: the number of detected animals, the size of the study area, the strip path width. And this is how estimates are obtained, for example, for the different dolphin stocks in this survey region, which you see in the top left. Of course, if you think in the context of dolphins, it's not usually single animals you detect, but you have clusters of animals. The dolphins occur generally in schools of varying sizes, and then that adds another level of complexity. We have to get an estimate of the group size. But we're going to focus here today on P sub A, so the proportion of animals detected in the covered area. Why do we care? Like I said before, there was a high mortality in the last century for various dolphin stocks, and particularly those two examples shown here, the northeastern offshore spotted dolphin and the eastern spinner dolphins, beautiful animals. And these abundance estimates from the different cruises, each one of these cruises usually took 120 sea days, generally conducted with 2 or 3 ships. And that results in these individual data points collected, which you see here in the left plots. So those abundance estimates also feed into population trajectories that you see here in the middle. This combines these abundance estimates with mortality data from the 50s and the 60s, for example, and you see that the dolphin populations don't seem to recover, hence the continued importance to conduct these surveys. So these are from the last decade, these publications, but recent evidence has shown that the trackline detection probability, what I explained earlier is highly important for distance sampling, was actually not perfect, but Jay Barlow published these estimates of what it really was. So instead of perfect detection, where this P0 was equal to 1, it was actually decreasing as a function of Beaufort sea state. Beaufort sea state being the viewing conditions, so the state of the ocean. So if there's more wind and you have more whitecaps, the higher the sea state. And of course, it's intuitive, it makes sense. The more waves there are, the harder the dolphins are to see. So this is what Jay Barlow provided. He didn't use the MARC recapture distance sampling method. So on a side note, which is what I'm going to explain next, but he used a simple regression where he regressed the encounter rate of these dolphin schools against various covariates. So there's a little discussion about whether we should take these for granted or not, these values. That as a side note. But the implications of if these estimates are true, then all these figures on the left will have to be reworked accordingly. So let's talk about what this MARC recapture and distance sampling is. So again, we have animals in the study area, we have a line, And now we have 2 observers, and like before, it's not individual observers, but I want you to think of them as observation platforms. So for example, 2 decks on the same ship, or we see different platforms examples later on. So again, both observers go along the line or drive along the line in the ship and make detections, both collect the distances to the animals. And now what happens here is we have additional information. So you can think of the observer 2 setting up trials for observer 1. So each animal that observer 2 detected is a trial for observer 1. Did observer 1 detect it or not? So that allows us to fit 2 types of models. We have the mark recapture model on the right, which is essentially a binomial GLM incorporating the trials and the successes and failures. So let's focus on that. So we can think of this histogram representing the proportions within the respective distance band of the proportion of animals that observer 2 and the proportion of detections made by observers 2 that observer 1 also detected. So that's what this yellow histogram is supposed to represent. And for example, in this first distance band from 0 to 10 meters, the histogram comes up to about 0.39. If, for example, observer 2 had 100 detections in that distance band, that would indicate that observer 1 saw 39 of the same animals, and so on. So on the left, we have what we had before, our blue detection function, but now we acknowledge that that's just a relative detection function, and we adjust this function using the P0 value from the binomial GLM. So this is our mark recapture distance sampling model. And as you can see, this allows estimating trackline detection probability. So those are the statistical methods we're going to need to keep in mind. But what I'm going to talk about from now on is different applications, how you can collect this type of data. So important to remember from this slide is that we need 2 observation platforms. They must not queue each other. So observer 2, for example, must not queue observer 1 in making any animal detections. And it's also important to be able to tell whether that is the same animal. For example, one of the first detections down, let's say this first detection made by observer 2, seemingly by both observers, is that indeed the same animal or not? Sometimes there's a time gap between observer 2 and observer 1 detecting the same animal, and the animal might have moved, so there's a difficulty in that part as well. So this brings me to the first application. This is a paper that we recently published. And here we had a visual and an acoustics platform. You see the track lines on the right. And so this was a shipboard survey for dolphins also in the same region. So here we had the visual team on the flying bridge of the ship, and the acoustics team was sitting inside the ship, but they were towing an acoustic array. So that means at least 2 hydrophones were attached via a long cable and towed behind the ship at about 300 meters. And both of them made detections at the same time. So you might think, how are we going to get the distances for either one of those 2 platforms? So for the visual team, for example, imagine the ship is moving along the line, and the observers see a dolphin out there. This is the quantity that we need, the perpendicular distance to the dolphin, but this is what we get. And so the radial distance to the dolphin and the angle alpha, this is what you can imagine we can get, for example, using these big eye binoculars. These are high-powered binoculars. They have a 25-powered magnification. And what they do have, if you look through the right ocular, you have this reticle scale, which you can line up with 0 reticles with the horizon, and then you can read the reticle scale. This is converted into a radial distance. And we also have an angle board here, which allows us to obtain relatively accurate angle measurements. So this is how we get them visually. And then under the black box, you would see the trigonometric function, how you convert the radial distance and the angle into a perpendicular distance. So how do you get your distances using acoustics? Imagine the ship is moving along the line and the dolphin makes a sound. And using the time difference of arrival of the sound between the two hydrophones, you can get an angle from the hydrophone to the dolphin. You don't know left or right, but for distance sampling, that doesn't matter. So as the ship moves along, you keep the first angle in mind on your map, and then the dolphin makes another sound, you get another angle, and where these angles converge, that's the location of the dolphin, and you can get your distance. Like I said, left or right, doesn't matter for distance sampling, we need the distance to the dolphin. So, and we use this method to estimate the fraction of dolphins missed by the visual observers for this particular species, the rough-toothed dolphins. These are not prone to react to the ship very much and were therefore suitable for this study. And on the right, these plots, you see the mark recapture distance sampling model without any covariates fitted to these data. We fitted also more complex models and conducted model selection. So you can see here the best fitting model had Beaufort in the mark recapture model. So this means that the detection probability on the track line actually decreased with the function of Beaufort, confirming J. Barlow's results. And these are our estimates. They're not exactly like J. Barlow's for this particular species, but they confirm that he is on the right track. So, next project. So in 2018, we at CREAM obtained the contract to design the next survey for Eastern Tropical Pacific dolphins, the study I mentioned right at the beginning. So in the first phase, this first contract was just to come up with a new design, what issues needed to be considered. And this trackline detection probability issue was right on top of the list. So in this report, we proposed to use MRDS with long-range drones. So here you can imagine that observer 2 is sent a little bit ahead of observer 1, so observer 2 being the drone and observer 1 being the ship. And then the drone flies in a zigzag ahead of the ship. It flies in a zigzag because it has the camera pointing down and it needs to cover a large area in front of the ship. The drone records video. We also had planned on using real-time observation on the ship. And yeah, so this was what we proposed. And of course, as these are new methods, we needed to test these in a trial survey. So in our report, we described that the parts that needed to be tested, of course, was how far ahead of the ship can we send the drone. So you see here, we suggested 5 nautical miles or more. This was due to that we assumed that this whole issue might arise because the dolphins are reacting to the ships. So they hear the ship coming from several miles away and they start running away from the ship. So we needed to capture the dolphins with the drone before they reacted to the ship, hence the long distance, hence the requirement for fairly heavy duty drones. So these are not the type of drones you just pick up at Amazon, but they're almost military grade drones. They needed to fly at least 5 nautical miles ahead of the ship and transmit the video in real time back to the ship for us to monitor in real time. So the drone would then fly in a zigzag pattern ahead of the ship. And we also needed to test at which height we can fly in order to obtain good enough resolution and cover a large enough area. So this brings us to the next phase. This was the second contract we obtained from IITTC, the actual implementation of the trial survey, which is what we did last year in November. So we came up with a study design. The research vessel we used was out of Mazatlan, which is up here in Mexico on the west coast. And you see the track lines we designed coming in and out of Mazatlan and taking us into this study area here where we expect the highest numbers of spotted and spinner dolphins in the whole Eastern Tropical Pacific. So that was good to have it relatively close to Mazatlan. And the purpose of the trial survey was, for, of course, to test the new research vessel and testing the drones, especially for our purposes, and also for school size calibration. But that's a topic that's not going to be part of this talk. So this is the research vessel kindly provided to us by the Mexican government, and pointed out here where the observation platform is, our Observer 1. So this whole, before I go on to that, to the next slide, in the back here you see the drone platform that was specifically implemented for this survey in order to launch and land the drones. So here you have a look at the observation platform where you see the 3 main observers scanning the horizon during all daylight hours. So this is Observer 1. This whole platform is Observer 1. And then this is how Observer 2 is launched. So you can imagine that launching a drone from a moving ship is not a trivial task. You see there's a lot of metal surrounding the platform, and but we had an extremely good pilot. This is this person standing here in front of us. His name is Kevin, and he is the he is actually the he makes it look like child play. Because he's the national champion for 3D helicopter flight in Taiwan. So it was very good to have him on board. Also, never a dull moment when he landed the drones for us, which we watched in real time on the video screen. So and this is on a relatively calm day. You can imagine that the ship moves a lot more when there's higher Beaufort Sea state. and the ship is rolling a little bit left and right. So imagine you had to land your drone on the back of a pickup truck that was going about 20 kilometers an hour over a bumpy road. So next, we're going to have a look at a little bit of video footage here. And I want to warm you up to the idea that sometimes you have to think with different hats on. So if you have the biology hat on, you might look at this footage and say, oh, this is very exciting. Killer whales. There's two little calves, and you might be interested in the behavior of the whales. If you look at it from with your statistics hat on, you might think about group size. Okay, there's 5. There's really no uncertainty about that. But if you think about it from an image analysis, with your image analysis hat on, and you have to start thinking about how can I write an algorithm that will automatically find these killer whales or any other dolphin in the remaining footage. What kind of information do I have, and what kind of problems will I encounter to detect dolphins in the footage? So you can see here, for example, as problems, you have a lot of glare and you have a lot of motion of the different waves. But the information that you do have is, of course, you know that for one, video is nothing but an accumulation of different individual frames at a rapid succession. So that's one piece of information. And you also know that each individual frame, the way it's stored, is a pixel by pixel information that's usually stored as a RGB value. And using that, you can see which pixels have similar information and find out what adjacent pixels form different shapes. So you see here a still frame of the killer whale footage you saw earlier with the shape of the left killer whale lined out. So you have the pixel information. Using that, you can create the shape information. And thirdly, you have the movement of the killer whales over time from frame to frame. So those are the 3 pieces of information you have. And now in the next few slides, I'm going to talk about work that Lewis McMillan, our postdoc, has been conducting and put together. So here on the right, you see actual footage from that survey with a group of spinner dolphins, where we're interested in getting the total count of the whole school. So it illustrates the points that they're extremely hard to count. We have about 100 hours of footage from these 2 weeks alone. And thinking about that, what follows this trial survey, or what should follow, is a 120-day survey. You can immediately see that it's not going to be possible for humans to go through all that footage, or even just to count the animals in this school. I've actually tried to count how many animals are in that school, and 4 attempts created 4 different counts. So I have a lot more hopes in the image analysis conducted by Lewis and Sakina. So what Lewis is doing, he's using a machine learning algorithm to detect dolphins in the videos. So what happens here is he generates a small data set from training footage where he creates objects of interest that might be dolphins, but are not dolphins for sure. So in the second stage then, Claudia has taken a lot of effort and gone through over 20,000 of these objects of interest and labeled them manually. So are these dolphins, are these multiple dolphins? Is it a whale or is it something else? So there was a lot of water splashes, but sometimes also turtles and birds in that data set that needed to be divided. And then in a third stage, this labeled data set is shown again to the machine learning algorithm. So the algorithm learns this way what are dolphins and what are not, and then you can use what is learned to make predictions for the remaining footage. So the problems we had encountered during the trial server was the relatively poor resolution of the video. So if you look at the large image, even though you only see rough shapes of dolphins, you can tell that they're probably dolphins, also because there's a bunch of them together. But if you zoom in, you don't actually have very good resolution. So that was the problem we encountered with the drone provider that we used. So, but what we're trying to get at is what you see here is red outlines around dolphins that the algorithm detected. So this is from the first stage, so before the algorithm had learned what is actually a dolphin or not. So once it has learned what a dolphin really looks like, we expect that all the dolphins in this image and all the other images will be detected. So just to lead into what Sakina is doing, like I mentioned before, we have a third piece of information, which is the optical flow, which is relates to the motion in the image over time. And this is an example from YouTube. You see that the only part in that video that are really moving are the arms of this man. So we're going to use the fact that the dolphins are moving in a certain way next. So this is what Sakina has been working on. And what happens during her analysis is the video is divided into frames. You subtract the stationary background from each frame, leaving you with certain pixels that are moving from frame to frame. The algorithm then draws contours around these objects, and then you measure the distance traveled of these objects over time. So, and in the end, K-mean clustering, you just cluster the objects by whether they move in a similar manner or not. So I'll explain this a little bit more detail in the following slides. So these are similar techniques examples. So you can see in the top, the application was to detect the moving cars in this image, in these images, and you can see that that's picked out as the only parts that are moving through the picture from frame 1 to frame 2. In the bottom example, we have a little bit more noise. I assume that was because the leaves were also moving, but it's mostly the shape of the cyclist that was captured using optical flow. So let's look at how this works for us. So in the left diagram, you see how this is done. So the circle in the left graph shows you an object, the outline of an object that's at x and y at time t. And then between the first frame and the second frame, certain amount of time passes and this object moves in, and this displacement in space is measured in pixels. So when you apply this technique to the dolphin data set, which you see here on the right, you see that this image is overlaid with a grid of tiny little arrows. And the arrows indicate the direction of the motion, and the size of the arrow indicates the speed at which it was moving. So you see the areas that appear to be greener in this image are the areas with the stronger motion. You see there's a lot of green around the dolphin we see here, but there's also a lot of green around some of the glare which was on top of the waves. And that leads me to the next level of the algorithm, and that was k-mean clustering. And here what happens is, let me see if I can give this justice. So if you think about waves and glare moving across the video footage, for example, from the killer whales earlier we saw, the waves and the water in general moves through the frame in a fairly constant direction. And it's also likely that you will pick up a lot more of these glare type objects than of dolphins. So the dolphins, on the other hand, they move at a different speed and likely in a different direction as well. So k-mean clustering means that there's an algorithm that clusters the objects based on the similarity of their movement, and then we can divide the dolphins from the water using this method. So that was up to now, that was image analysis. So what do we actually do once we have the detections of dolphins from the drone? How do we convert this into Mark recapture distance sampling data? So the next challenge, of course, is to determine which ones are the duplicate detections, which dolphin schools detected by the drone were the same ones that the ship observers detected. So, for example, in this example, was dolphin D1 the same as dolphin D2? Because the drone came through much earlier than the ship, it is very likely that the dolphin will have moved in the time that lapsed between. So we need to come up with a method to determine whether those are the same dolphins. And here we can, of course, use the separation in space and time, because we have the location for both sightings, and we of course have the time, but we can also use information on the species, the number of animals in the cluster, and the general behavior, and a few other things to make that decision. So, next step, there's not a lot of text here because everything is a little bit on hold at the moment because of COVID. That's why I decided to put my favorite landscape picture from the trip here. But of course, I mentioned earlier that we encountered some problems with the video footage provided by the drone company, and so we proposed to do more testing at sea. That was supposed to happen this November, but it's now postponed. And the plan was to do a main survey next year, a full 120 sea day cruise, but that might be postponed as well. So now I need to check the time. I probably have some time to talk about the third application Okay, so here this is, now we need to move away from dolphins and line transects a little bit and talk about a fully acoustic survey in which mark recapture distance sampling methods apply as well. So this is the title you see here is the title of a method comparison paper that I just submitted. So it's very much work in progress, where we compared 3 different methods for estimating call abundance of bowhead whales using passive acoustic monitoring data. So one of the 3 methods was distance sampling, and what I'm showing you in the following slide is an add-on to this. So first, where was the data collected? So this is a large-scale acoustic study that's conducted in the Beaufort Sea up in Alaska, where they deployed DASRs. These are directional autonomous seafloor acoustic recorders at 5 different sites during the fall migration of bowhead whales. They come through that area every fall, and the interest here was to determine if the oil industry who are mining in that area had an effect on the migration of bowhead whales. So each one of these red dots is the location where one of these DASRs was moored. And how does this work? So first, a little bit about what the difference in general is between what we're looking at now and the study before. So before we had line transect surveys, and now we're talking about point transects. So this is also a part of distance sampling, but instead of walking down the line, an observer is stationary, like our sensors from the previous, like the DASRs from the previous slide. So here, observer is stationary for a time and makes detections of animals or animal calls in the acoustic sense within a certain radius, indicated here by the yellow circle. So we also need the distances to the detections. But for point transects, we also assume perfect detection on the point, on or near the point. This is the critical assumption here. So how does mark recapture distance sampling work for point transects? You need 2 observers, so not at the same location, because they must not queue each other, but slightly separated in space. But for the acoustics, the extra challenge is that they need to be able to detect the same sounds, or in this case, the same calls made by the whales coming through. So not only is it important that observer 1 and observer 2 can hear the same calls, but you also need to be able to tell, is it the same call or not? So, but due to recent advance in technology, we're able to do this now, and therefore we can collect this kind of data. So you would end up with data like this, where both observers make detections. Of course, for mark recapture, if you try to determine the detection probability at the point for observer 1, you need to get the distances of all detections between observer 1 and the detections. So this includes the detections made by observer 1 and made by observer 2. And for that reason, you need to be able to localize the detections. So this is the data we have available from the bowhead whale migration study. So this is how this works. You see here on the left, the configuration of the 7 DASRs, at a particular site. You see the whales coming through, and some of the whales don't make any sounds. Some make sounds and are undetected. But let's look at this whale here, whale 2, who makes this call, and that's detected by 3 sensors. So these sensors, these dasers, they measure the angle from the incoming call, and once you have 2 or more angles, you can actually localize where that call was coming from. So, and the way this is done usually is you look at these manual observers, human observers, looking at these spectrograms from the 7 different channels and compare, okay, was this call detected on the other dasers, and so on. So this is where this data comes from. And then you can start thinking about these dasers as a mark recapture distance sampling type experiment, where if you want to assess if daser A has perfect detection on or near the point, then, or let's say within 4 kilometers around A, you can do a simple first exercise and look at, okay, how many calls were detected by any dasers within that radius around A, and how many of those did A detect? So only 95%, so that means it didn't have perfect detection within 4 kilometers. Similarly, for daser B, you can do the equivalent. And here we see that it was doing slightly better. It detected 98% within 4 kilometers around B. You can also do a bit more complicated analysis, more complex, and look at, so on the left we have the number of calls that were localized within the different areas of this dartboard type chart here. So over here in this area you had more calls that were detected, but more interestingly, over here you see the proportions, so you can determine which parts around the daser lacked in perfect detection. So the worst areas here being the lighter reddish colors. Similar for daser B, it seemed like it was doing a lot better, but there's still some areas here and here where the detection was not perfect. So this is a relatively new application, and just to sum things up, the important messages here are it's important always to check your assumption. When you use a statistical method, you need to make sure that your assumptions are met. And I find this a particularly exciting area with these new applications available for existing statistical methods, including MRDS. And it's important, like I said before, to be able to switch hats a little bit and see what kind of new technologies are out there, what can we make use of. But of course, there's a lot of potential issues, non-independence between observers. How can you actually make sure they don't cue each other and they don't react to the same cues? Identifying duplicate detections is going to prove very tricky for the drone survey. Responsive movement is very tricky in determining the distances. For example, you need to capture the distances before any of these animals react to the observer coming. That's tricky for dolphins that react to the ship. And with that, I would like to acknowledge the funders for the different studies. And thank you very much.
Thank you very much, Julia, for that really interesting talk, particularly on integrating different methodologies and statistics to achieve like a common goal. We have now time for questions. If anyone has any questions, please write them on the chat box. I will read them out loud. Or if you prefer to do them, how would you prefer to do that, Cornelia?
Sorry, I didn't hear the question.
So would you prefer me to read the questions?
Yes, that would be nice. Yeah. Mm-hmm.
I'll give a couple of seconds for people to type down their questions, but I do have a couple of questions. It was really interesting, particularly the part about the drones. I was just curious about how high it was, the drone, and how did you decide for the optimal height? Was it to try to capture the whole group or try to make sure that you could identify individuals?
So the drone flew at different heights, but never lower than 60 meters. This was for several reasons. One was, of course, that we wanted to avoid that any dolphins would react to the drone. That wouldn't be beneficial for our study, and we don't want to disturb the dolphins by the drones. So this is actually an important issue. We try to be as non-invasive as possible with this, and I had to put this into the ethical approval for this study, that we weren't going to fly lower. But also, when you use a long-range drone like that, you have to fly at a certain height, otherwise you lose the signal to the drone. So the signal going back and forth between the ship and the drone, and then you have potential of losing the drone. But that said, I mentioned that there were two different objectives for the drone research. One was the track line detection probability, and one was the school size calibration. I'll start with the track line detection probability. So here, that's the part where the drone flies in the zigzag head of the ship and needs to make detections. So for that, the higher you fly, the more area you cover, and that's in your best interest. That gives you the highest chance of capturing any dolphin in that footage. So the lower you fly, the narrower is your viewing angle, and the less area you cover, the less detections you make. But that comes at a certain cost, of course. With the poor image resolution that we had to fly at 100 meters altitude, and that also had an effect on the speed we could fly at, because the drone was able to fly at 80 kilometers top speed, but at 100 meters flying at 80 kilometers, you don't actually see anything anymore. It just rushes by too quickly. So we had to reduce it to 30 kilometers per hour, reducing yet again the amount of area covered in front of the ship. And the whole thing led to the flying bridge observers, the ship observers, making a lot more detections than we did with the drone. So those are all things that we had to test and evaluate from the trial survey. So with the calibration, there, of course, you need to fly over the school. There the interest is to capture the entire school with good enough footage to where you can get to the true number of the school. That means it's ideal when the school is relatively compact and is near the surface and doesn't move up and down a whole lot, and when you can capture the whole school in a single frame. But like you saw that the spinner dolphins, it was a long, drawn out school where we tried to get the whole school in a sweep. So there you fly over the school. Like if the school has an oval shape, you kind of take the drone over the school at a relatively slow speed, because you need to give the dolphins the chance to come to the surface at least once while you fly over. That was a long answer to your question.
No, it was excellent. Thank you very much for that detail. We do have a question from Patrikas. He's asking the drone used to acquire image, did it use polarized filters, and does that interfere with downstream image analysis?
So we used filters sometimes and sometimes not. I think during the spinner dolphin footage, there was a filter on, but the killer whale footage didn't have a filter on. So this was also part of the testing. What is the best method to cut out the glare, which is a big problem, but it's different. This problem changes with the time of the day, with the sun angle as a result of time of the day. So there's not a like one solution that is always right. So you need to take into account the time of day, like I said before, and also whether it's an overcast day or a sunny day, what is the sea state, all those things we still have to learn a lot about. When is the best time to put the filter on and when not. But for image analysis, I'm not sure if it will affect the results much. I mean, once the glare is cut out, I'm not sure if, I mean, if the glare is cut out, of course, that's beneficial. But I'm not sure whether there is a solution, whether the one thing is better or the other, like on or off is better than the other from an image analysis point of view. So I need to check that with Louis and Sakina.
Thank you very much. We have another question from Nick. I wonder if using pairs of drones monitoring the same area, but information might help with removing spurious detections and covering a wider area, although it will be more expensive.
What do you mean with spurious detections?
Nick, if you want to come on.
Can you hear me?
Mm-hmm.
So it seemed it was a really nice talk, and when you showed the pictures of the dolphin detections, both in the optical field, but prior to that in the sort of feature detection steps, it seemed like, to my somewhat naive eye, I guess, that there were quite a lot of features that looked quite a lot like dolphins that were not being picked up, certainly in the feature detection step, but also a little bit in the motion detection step. And so I'm just wondering if having correlated pairs of observations might help remove any false positives from things like glare, because you'll have two different viewing angles, and so the glare will be different, but the dolphins will be the same. And might also help you with the motion, because you'll have two different perspectives on the motion.
You mean if you have two different cameras on the same drone and get two different
or two different drones. So I think if you have two different cameras on the same drone, that might not help you very much, because the glare, for example, will be pretty similar. The perspectives are pretty similar. But you can imagine flying two drones, both looking at the same patch of sea, but from quite different angles, and seeing the same dolphins, but seeing a different pattern of other features that might be detected spuriously with individual drones.
Yeah, that's probably a very good point, but I'm not sure. I have a hard enough time to find sponsors to sponsor one drone, and that's in the budget is the price tag that comes right behind the ship. So it's very expensive to fly these drones. And it also increases the risk. So making sure that, imagine two drones flying next to each other fairly closely at 5 miles ahead of the ship and not crashing into each other. So I think there's some safety concerns that would be added on top of that. But hey, why not think wild? And it's definitely a good idea. Maybe in the future we can consider these when standards still improve. Maybe even 2 cameras on the same drone. Maybe something can be done with that. There's actually great systems out there. I'm by no means an expert on drones and cameras that are out there, but I've heard a little bit about the different options, and there's some really cool stuff out there. So you never know.
Thank you very much. I don't think we have any further questions. It is now, I just want to thank you again for this amazing talk. It is now time for lunch. So we have a new different Teams link for the afternoon session. I don't know, Alte, if you want to say any words before.
Well, just thank Cornelia for a fantastic talk. Such a challenging sort of data you're dealing with, and I love the idea that you are balancing these 3 hats: the statistical, the biologist, and the image analysis. So no, I don't know. Yeah, I just thank you for your time and for the lively discussion as well. It's been great. So yeah, we'll see you all at 2 for the next talk and the closing remarks and the prize awarding. And yeah, please use the other link to join that. Thank you.
Thank you.
Hi now.